So, what's the deal? How do you really build a brand new molecule from an existing one? Is it all just, bubbling potions and chaos, or is it something a lot more precise? Well, let's find out.
Oh, it's definitely a recipe. And the one we're following today is all about giving a molecule called aniline a complete and total makeover.
Okay, let's get into it. First up, our starting lineup. Just like any good recipe, you've got to know your ingredients and what you're trying to make.
So here's the game plan. We're starting with this stuff, aniline. It's a pretty simple aromatic molecule. Our mission, should we choose to accept it, is to very precisely stick 3 bromine atoms onto it. The goal? To transform it into a totally new substance called 2,4,6-tribromoaniline. But, there's always a catch, right? Aniline is, well, it's a little too eager to react. See that phrase, strongly activating? That's chemists speak for, this thing goes wild. It can get out of control really, really fast. So our biggest challenge isn't getting the reaction to start, it's taming it.
And here are our key players. Now, you're probably noticing a theme here. Corrosive, toxic, irritant. Yeah, this is absolutely not kitchen chemistry. This is serious stuff. Working with these reagents means you need major safety precautions. The whole thing has to be done inside a special ventilated box called the fume hood to make sure none of those dangerous vapors get out.
Okay, so we've got our ingredients. Now, how do we put them all together? Let's walk through the actual step-by-step recipe for this molecular makeover.
So, if you write it all out as a chemical equation, this is what it looks like. You take one aniline molecule, react it with 3 bromine molecules, and boom, you get our target, the tribromoaniline, plus a little bit of hydrogen bromide as a byproduct.
All right, this breaks it down into 4 key steps. It's super important. First, the setup. We dissolve our aniline and chill it way down in an ice bath. This is all about slowing down that crazy reactivity we talked about. Then, the addition. We add the bromine super slowly, literally drop by drop while stirring. Control is everything. Once the reaction's done, we isolate it. We just filter out the solid stuff that's formed. And finally, purification. We clean it up to get those beautiful, pure white crystals.
Okay, now for my favorite part. This is the big reveal. This is the moment of creation where we actually get to see our new molecule pop into existence right before our very eyes.
So as we're adding that bromine, drop by drop, this is it. This is the moment. A dense white cloud, a solid, just appears out of nowhere in the liquid. That solid is called a precipitate, and it's the very first visual proof that our new molecule is being born. It's awesome. And that white stuff, that's not just some side effect. That is our product. That's the 2,4,6-tribromoaniline we set out to make. See, it's not soluble in the acid mixture, so it literally crashes out of the solution as a solid. It's the ultimate confirmation that our recipe is a success.
But hold on. In chemistry, making a white powder is one thing. How do you know for sure that you've made the right white powder? I mean, it could be anything, right? Well, this is where the quality control phase kicks in.
We've got to answer 2 really important questions. Number 1, is it pure? And number 2, is it actually the right stuff? Thankfully, chemists have some tried and true tests to figure that out. And one of the absolute classic tests for purity is checking the melting point. Think of it like a chemical fingerprint. Every pure compound melts at a very specific, sharp temperature. For our brand new molecule, that fingerprint temperature is 122 degrees Celsius. So the test is pretty straightforward. You measure the melting point of the crystals you made and compare it to the official known value, what we call the literature value. If your stuff melts nice and sharp, right around that 120 to 122 degree range, you nailed it. That's a huge sign of a successful and pure product.
Another thing we check is the yield. This basically answers the question, how efficient was our recipe? It's a percentage that tells you how much product you actually got compared to the absolute maximum you could have possibly made. In a typical lab, getting a yield of around 65%, that's a really solid result.
All right, so we made a specific white powder. We proved it was pure. But so what? Why does this one little recipe matter in the grand scheme of things? Well, let's zoom out and look at the really cool big picture idea that this whole experiment shows us. This whole process is a classic textbook example of a reaction called electrophilic aromatic substitution. I know, that's a mouthful, but here's an easier way to think about it. That little amino group on our starting aniline molecule, it acts like a powerful director on a movie set. It points to 3 specific spots on the molecule and tells the incoming bromine atoms, you go there, and you go there.
It's that incredible level of control that makes this type of reaction so powerful.
And look, this idea of directing atoms to exact locations on a molecule, it's not just some cool lab trick, it is a cornerstone of how we design molecules today. This fundamental principle is used to build the incredibly complex structures we need for, well, almost everything. We're talking pharmaceuticals, dyes, polymers, even agricultural chemicals.
So it really does all come back to that recipe, doesn't it? Learning these rules of molecular construction isn't just about following steps. It's about understanding how to build. It's about gaining the power to create. And that leaves us with a pretty incredible thought. If you can precisely control where you add every single atom to a molecule, what are the limits? What can't you build?